Alright, section 4.4 notes, the multiplication rule. Now we're dealing with multiplying to come up with probabilities instead of adding. So now we're going to be compounding events, multiple events, with the word and instead of or. Usually when we do this with two events A and B, we talk about event A occurring in the first thing we're going to do, and then event B occurs after that in the second thing. So what we have to be wary of and be careful about is, does event A cause event B to change, affect its probability? And if it does, we have to make sure to make that adjustment when we compute these. Alright, now to illustrate this idea, I'm going to show you what we call a tree diagram. Tree diagram is basically a way to come up with the sample space. So let's do a tree diagram for true-false question followed by a five choice multiple choice question. So this is every single possible outcome of those. So if the first answer was true, the second answer could have been A, B, C, D, or E. So that gives us true A, true B, true C, true D, true E. Or if it were false, we could have A, B, C, D, or E. And that would give us false A, false B, false C, false D, false E. So these are all my possible choices. So we get 10 possible outcomes here. So this is the sample space for this compound event here. A true-false question followed by a multiple choice question with 5 choices. Alright, so that's what a tree diagram does. It gives us a link from choice 1 to the others. Choice 2 or event 2. Alright, let's try it. A couple plans to have 3 children. Construct the sample space of all the possible gender combinations. So we're assuming this is before they've had any. So instead of just blindly guessing, okay, boy, girl, 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 like all the different combinations, a tree diagram will guarantee that you get them all covered. So I start with a dot, and then I make a branch to each possible choice for the first child. So the first kid could have been a boy, or the first kid could have been a girl. And then from each of those first choices we branch off again. So the second kid, if the first one was a boy, could have been a boy or a girl. And then the second kid, if the first was a girl, could have also been a boy or a girl. And then from each of these possible second children, we get the possibility of a boy or a girl. So you see it's doubling the number of branches every time we go off to the next child, because of the fact that there's 2 outcomes each time. Of course, it would be more or less depending on how many outcomes are possible at each stage of the process. But then you just follow the branches at every path you can take to get all your possible outcomes. So if we take the top branch, we get a boy, boy, boy. If we take the second one, we get boy, boy, girl. If we take this, we get boy, girl, boy. And then boy, girl, girl. And then finally we move down to the girls first. Girl, boy, boy. Girl, boy, girl. And then finally girl, girl, girl. Oh, sorry, girl, girl, boy first. And then girl, girl, girl. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8 outcomes here. And 2 to the third is equal to 8. So that's where these come from. 2 meaning there's 2 outcomes for each child. 2 to the third equals 8. Now you can only do this to get your number of outcomes if it's the same number of possible outcomes at each stage of the process. Okay, if we were talking about, rolling a die, then flipping a coin, and then drawing a card, we couldn't just take something to a power, but we could multiply to get those possible outcomes. Now I could be asked, what's the probability of having one girl? Exactly one girl. Well, I would go through here and find all the things that satisfy one girl. Alright, and only one girl. there's 3 out of 8. Okay, so 3 possible ways that it's satisfied divided by the 8. Alright, now I could also do something like probability all 3 are boys. Alright, if probability all 3 are boys, well, that's this top one, and there's nothing else that has all 3 boys, so 1 out of 8. Now, we'll have to get into these later on, one girl, because there's multiple ways that can happen, but there's only one way that this could happen. And right now we could introduce this multiplicative rule with that idea. If I wanted to find the probability all 3 are boys, now this is assuming that it's equally likely to have a boy or a girl. So we get that this is the same thing as saying the probability of a boy and a boy and a boy. And you may be thinking, why is he writing it like that? Well, because with this AND rule, this multiplication rule, if I'm trying to find the probability of 2 events joined by AND, it's multiplication. So everywhere I see the word AND, I'm going to multiply. And basically I'm going to break this down into one compound event into the probability of each individual event multiplied together. So we get the probability of boy times where the AND is, probability of boy times where the AND is, probability of boy. And if you multiply that out, or if you find those individual probabilities, you end up with a half, alright, for each one, and a half times a half times a half. Remember how we multiply fractions? We multiply straight across the top and we get a 1. And we multiply straight across the bottom. 2 times 2 times 2 is 8. And we get an eighth. Now, that's the same thing we got right here. Again, this one right here will have to wait because there's more than one way for it to get that outcome. But it's not that much harder. It's 1 half, 1 half, 1 half, because it's still the probability of each one of these is a half. So that's 1/8. That's 1/8, and that's 1/8. But this could happen, or this could happen, or this could happen. And remember, when it's or, we add. So 1/8 plus 1/8 plus 1/8 is 3/8. Okay, but there is going to be an easier way to do that later on. But you could even do it now with just using the and the or probabilities. Alright, now key point here, we must adjust the probability of the second event to reflect the outcome of the first event if they are dependent on one another. So if the second event changes if the second event changes based on what happens with the first event, then we do have to make an adjustment to that second event's probability. So for example, find the probability of the top 2 cards in a shuffle deck are diamonds. So this is saying if you find the probability of the first being a diamond and the second being a diamond. So even though it doesn't necessarily say and in the original wording, we can figure out a way to say and. Now we can use that rule. Okay, so it becomes find the probability the first is a diamond multiplied by the probability the second is a diamond. So that and is going to become multiplication. The probability the first is a diamond, well, there's 13 diamonds out of the 52 cards in the deck. Then we move to the second card being a diamond. Well, this card, because it was the top 2 cards, this card, we're no longer considering it anymore. So there's only 51 cards remaining. And because the first one was a diamond, for this one to also be a diamond, there can only be 12 diamonds remaining. Okay, now because we're multiplying fractions, reduce the fractions first so you get the smallest numbers you can. Okay, 13 goes into 52 4 times, so we can reduce that down to a fourth. Alright, and then over here, if you don't know if 12 has anything in common with 51 or not, we do know that 12 has something in common with 4, and remember we can cancel diagonally. Okay, and then 3 does have something in common with 51. 5 plus 1 is 6. 6 is divisible by 3, so that means 51 is also. So I'm going to take 3 and go into the 51, and if you do that, you'll get a 17. 3 goes into 51 17 times. And then the only thing left up top is just a 1. The only thing left on the bottom is a 17. So there's a 1 out of 17 chance that the top 2 cards are both diamonds. Now, of course, that would relate to both hearts, both spades, both clubs, but there's a 1 in 17 chance that the top 2 cards are from the same suit. Alright, so just to reiterate, when we have that conditional probability, condition meaning, like in the last example, that the first card was already a diamond, we have to adjust for that second event. Okay, this event has already occurred. We subtracted 1 off the denominator, we subtracted 1 from the numerator, and that gave us our new probability for the second event B there. Alright, and then this is notation for conditional probability. So we use probability of parentheses B just to say, alright, find the probability B happens. Okay, but we put a little line and then another event beside that line to say, alright, find the probability B happens given, we usually read that line as given, event A has already happened, or we read it B given A. Find the probability of B given A. But we're saying that this event has taken place, this event has transpired, we know what happens, we know the outcome, now find the probability of B. Okay, now if we go back to this example that we just did a little bit ago, this is actually a conditional probability. Instead of saying it's the probability the second card is a diamond, period, it's the probability the second card is a diamond given that the first card was a diamond. So what we found was the probability the second was a diamond given the first was a diamond. That's the probability we just found. So that probability the second was a diamond given the first was a diamond, because the first was a diamond, again we reduced it down to 51 cards, and because the first was also a diamond, there was only 12 diamonds left. Okay, now that was with replacement, without replacement, without replacing that card back in there. If we had replaced it, then we'd be back to 13 out of 52. So sometimes a conditional probability doesn't change the probability of the event. So if we would have put that card back in there and reshuffled the deck, now we're right back to 13 out of 52, and the fact the first was a diamond didn't affect it at all. Alright, that comes back to this definition, dependent and independent. Two events A and B are independent if the occurrence of one doesn't affect the probability of the occurrence of the other. So if I would have put that card back in the deck and reshuffled it, now the probability the second card is a diamond is the same as it would have been no matter what happened with this first card. If I draw a diamond, I shuffle the deck and then put that card back in there, shuffle the deck, the probability I draw a diamond is back to 13 out of 52. Those events would be independent. But if I pull out that card that I drew a diamond, I pull it out, now the probability is 12 out of 51, which is not equal to 13 out of 52. Alright, we decreased the denominator and the numerator there, and so we're changing the probability of the second event. Okay, that's what this top thing's saying. Alright, if A and B are non-independent, they're said to be dependent. So in that case, what we were doing up here, this is dependent on this, because if I would have not drawn a diamond, there'd still be 13 here, and we'd be saying 13 out of 51. But because I did draw a diamond, it's 12 out of 51. So the probability the second card is a diamond depends on what happens with the first card. Alright, that's dependency and independency. Alright, and from that we get what we call the formal multiplication rule, which says if you're going to find the probability two events A and B, which are two events joined together by and, then we multiply, but for the second event we always use a conditional probability. The probability B happens given A happened. Right? Now if they're independent, the probability of B given A is the same as probability of B, and it would just simplify down to the probability of A times the probability of B if they're independent. Okay, so if they're independent, we just simply multiply the probability of the two events. But if they're not independent, if there is this dependency on the two, then this rule will work. Now this rule actually takes care of both, because when these are independent, we get this from it anyway. So this is the rule to remember. This is the rule to be able to practice and use. Alright, and then for independent events, or even for dependent events, if we have more than two outcomes, we can still continue the process. So find the probability. I roll a tail, a face card, or draw a face card, and have an odd roll on the die if I'm doing these three things. So that comes down to the probability of tail and a face card and an odd roll. So it's all about multiplication. And as everybody see, these things are independent. What happens with this, my roll on a heads or tail, is not going to affect this, and what happens here is not going to affect this. So these are all three independent events. So the probability I get a tail, not tall, tail, is equal to a half, and a face card, there are 12 face cards divided by the 52 cards in the deck, and then times an odd roll is a 50-50 shot, so a half. So I'm going to reduce. You could have written this 3 out of 6 initially and then reduce it. I'm going to reduce all of these. 12 out of 52 will reduce to 3 out of 13 times a half. And I see now that there's nothing that's going to be able to reduce vertically or diagonally, so I just multiply. Straight across the top I get a 3. Straight across the bottom I get 2 times 13 times 2 is 26 times 2 is 52. So there's 3 out of 52 chance that this series of events happens. A tail followed by a face card and an odd roll. Right, not a very good chance, even though 2 of them were 50-50 chances. This middle one wasn't that likely. Alright, and then the big summary. The addition rule, the word or suggests addition, and multiplication, the word and suggests multiplication. So when we're finding probabilities of compound events, we're looking to see if the word or and are already there. If they're not, we're looking to reword the phrases to try to get those words in there, and then see if we can compute those probabilities given the or and the and in there to hint at what operations we need to do to find them.